This is a walkthrough of Problem 3 on Practice Exam 1 of Module 8 in the book Problem Solving Guide for Mechanics and Thermodynamics. We have a uniform 100-gram meter stick lying at rest on a flat, frictionless surface. 5-gram dart is shot 75 centimeters. At the 75 centimeters mark, at a right angle to the meter stick at 50 meters per second, it sticks into the meter stick. What is the angular speed of the meter stick after the dart hits it? What is the translational speed of the meter stick after the dart hits it? So here's our diagram. This is the top view. The stick is lying flat on a frictionless surface, maybe an air hockey table. Here comes the dart. It hits it 25 centimeters from one end, 75 centimeters from the other end. It sticks to it. As a result, the meter stick is going to translate this way and spin this way. Spin counterclockwise as it moves to the right. This is an inelastic collision. The dart's going to stick into the meter stick. We know we're going to generate thermal energy. There's no external forces. We can conserve linear momentum. There's no external torques. We can conserve angular momentum. The meter stick actually is going to rotate about the combined center of mass. So this is going to stick in here. And as soon as it hits and sticks in here, the center of mass of the two, the center of mass is not at 50 anymore because there's a dart in it. It's going to wobble a little bit. The center of mass is 48.75 centimeters from the end with the dart in it. A little bit lower than 50. But we're going to make the reasonable assumption that the meter stick is going to rotate about 50 centimeters, the middle, after the collision. So we're going to make an assumption. It's going to make the answer a little bit off, okay? Because we're not going to calculate the moment of inertia of the meter stick about 48.75. We're going to just use 50. We're going to assume it's rotating about the middle. So let's conserve angular momentum about the center of the meter stick. The initial angular momentum is just of the dart. The meter stick's not moving. It's 25 centimeters away. That's the horizontal distance from the velocity. So we have the mass times the speed times the horizontal distance, and we get 62.5 grams meter squared per second for the initial angular momentum in the system. The final angular momentum of the system is going to be the same. The dart's going to hit it right here, and it's going to spin as a result. It's going to be I omega. I is the moment of inertia of the dart in the meter stick, assuming it's rotating about the center. So we have the moment of inertia of the combination of the center. So this is 1/12, which is a rod about the middle, 1/12 ml squared. And this is the dart. The dart is all, it's just ml squared. It's all at 25 centimeters. So we add these up, and we get 8.96 grams meter squared for the moment of inertia. Now we can set the initial angular momentum equal to the final angular momentum. There's the initial, which we calculated of just the dart. Final is I omega, and we calculated I. It's that. So now we can get omega, 7 radians every second. The meter stick's going to be spinning. That has nothing to do with the translational speed. That's only the rotational speed. Now part B. For this, we use conservation of linear momentum. The initial momentum is only of the dart, and that's mv. Mass is 5 grams, speed 50 meters per second. We get 25 gram meters per second, and this is a vector, so it's to the right. You don't have to pay too much attention to the vectors because we know the meter stick is going to be going to the right after the collision. The final momentum is mv, but here we have 105. It's 105 grams times v final. Because now the meter stick of 100 grams has a 5-gram dart stuck in it. So setting these equal, solving for v final, we get 2.4 meters per second. The center of the meter stick itself is going to have a little wobble in it because the meter stick is going to rotate about 48.75 centimeters, but we know the average has to be 2.4 meters per second to the right. The meter stick is moving 2.4 meters per second to the right on the average. Note, it's a very common mistake. Once you calculate omega in part A, to use V is omega r to get the speed in part B. And students do this when they don't understand that what V equals omega r means. That's a very specific situation when it's rolling without slipping. There's no relationship between V and omega in this problem. Meter stick is not rolling without slipping. If the dart hit close to the center, right? Close to the center, the angular speed is not going to rotate that much at all. So V is going to be bigger than omega r, right? The speed is fast and the rotation is slow. If the dart hits at the end of the meter stick, now it's going to have a lot more spin. So V is going to be less than omega r. If you understand where the equations come from, you're much less likely to misapply them. And that's the goal of the course. Understand. That's problem 3.